Hello everyone, thank you for joining me in this video where we're going to be covering competitive inhibition. This is part one in a series that I'm going to be making on enzyme inhibition overall, and let's begin. Competitive inhibition is one of the ways that we can actually introduce a molecule which can influence the overall function of an enzyme. Now, in competitive inhibition, we have something that we really want to emphasize, and that is the presence of a competitive inhibitor. Before we get into that mechanism, let's first talk about how an enzyme works in general. First, we like to see that we have our enzyme and our substrate occupying the same spot. They're in the same general environment. We can see that actually here as well. Our enzyme and substrate are in the same general area. And once they come together, we form this thing called the enzyme-substrate complex. And in this enzyme-substrate complex, we actually see that the enzyme is kind of orienting the substrate in a specific direction and allowing for that reaction to occur. Now remember that an enzyme is just a catalyst. It is not chemically changing or altering anything. It's just allowing this reaction that normally would have happened to happen just a little quicker than normal. Now, once this reaction happens, we end up with this final state. We end up with our substrate having turned into our product. This is the overall story of an enzyme. Now, in a competitive inhibitor, we actually see a very interesting story being told as well. We have a competitive inhibitor, and this inhibitor looks a lot like our substrate. Now, this competitive inhibitor is going to actually try to fight for the same spot. It's going to do its best to get into that same catalytic site. Now think about it like this. In a competitive inhibition scenario, we can expect that inhibitor to bind to the same catalytic site and prevent our regular substrate from binding. When this happens, the reaction that we're expecting to occur no longer occurs, and that is the general story of competitive inhibition. However, there is an extra and very interesting caveat, and this is based on the concept of competition. This caveat is that concentration equals competition. When we look at a competitive inhibitor, we need to realize that the concentration of our substrate can equal winning that competition. We can outcompete our inhibitor. So what does that mean? When we look at an enzyme and the enzyme has no substrates in its immediate environment, is there going to be any reaction occurring? No, not at all. So the more we increase the concentration of substrate, the more likely it is for one of these substrates to find its way to the catalytic site of our enzyme and actually undergo a reaction. The more and more, the greater that likelihood. The same is true for inhibitors. The more inhibitors we end up having in our overall solution, increasing the concentration of that inhibitor means that our inhibitor will have just as much, if not a greater chance of actually being able to hit that same catalytic site. So, what can we do about this? Just continue to increase the concentration of our substrate. If we continuously increase that concentration, eventually we'll overcome the effect of this inhibition because we'll just have a much greater chance of our substrate actually binding to our enzyme. Now, how does this influence some of the major components that we need to consider when it comes to kinetics? Things like our Vmax, our Kcat, and our Km. Well, our Vmax is the turnover number, but not of one enzyme. Think of it as the turnover number of the entirety of all the enzymes in that solution. The way that you can think about Vmax is, remember that when you're working in a lab, you can't micropipette an individual enzyme. You have to work with a multitude of enzymes in your solution. So Vmax is that turnover number, but multiplied by the total number of enzymes you're working with. So if we can outcompete our inhibitor by increasing the overall concentration of our substrate, what happens to our Vmax? Well, it stays the same. It doesn't change at all. You might be thinking to yourself, how? How is that possible? Well, let's draw out a graph. We have our concentration of substrate as compared to our rate of reaction. Our uninhibited enzyme, the curve that represents its kinetics is probably going to look something like this, right? Versus our inhibited enzyme is going to look something like this. We're going to get to that same Vmax because we were able to outcompete the inhibitor over and over and over again by just increasing that concentration of substrate. Suddenly our Vmax actually ends up being the exact same. Now what does that mean for our Kcat? Well, if our Vmax stays the same, shouldn't our Kcat be the exact same in that case? Shouldn't it also follow that same pattern? Well, for the case of competitive inhibition, actually yes, right? We are overcoming that concentration of inhibitor, and suddenly all we got to really worry about is, can the substrate bind to our enzyme if we have enough of our substrate in the solution? And if the answer is yes, we catalyze the reaction as always. So yes, our Kcat actually ends up staying the same. And what about our Km? So our Km is a slightly different story. So remember that Km refers to our Michaelis-Menten constant. This is the value that we attribute to affinity, right? The higher your Km is, the lower your affinity, and the lower your Km is, the higher your affinity. The reason why is because we're looking at the amount of concentration of substrate required to get to half the Vmax. So let's say our Vmax in this case, let's give an arbitrary number. Let's say that it's 80, right? And we're looking for half the Vmax, and it's around here, and that's 40. Well, we need to find the concentration of substrate that correlates to that speed of 40. Let's say that's 40 molecules per second, right? Well, if we look at our inhibited curve and we look at the Km that is attributed to that inhibited curve, we see that it's much further along our x-axis, meaning that it required way more concentration of substrate to get to that same rate of reaction. When we look at our uninhibited enzyme, it took way less concentration of substrate to get to that same rate of reaction, which means our competitively inhibited enzyme has a lower affinity, meaning it has a higher Km. Just to emphasize one more time, it has a lower affinity. So the last thing I want to talk about is the Lineweaver Burke plot for competitive inhibition. Now, when we look at a Lineweaver Burke plot, remember that the x-axis refers to 1 over our substrate concentration, and our y-axis refers to our 1 over our V0. Now, the intercepts are incredibly important. We need to remember that our y-intercept refers to our 1 over Vmax. And our x-intercept refers to our -1 over our Km. So this is great information. This lets us know where are we going to find our affinities and our Vmaxes. When it comes to competitive inhibition, we got to remember that our Vmax stays the same. So despite the fact that we're looking at a 1 over our Vmax, if it's the same number, it's the same number. So whatever line we end up with should be in the same exact spot, right? So we can essentially put a dot right at that same intercept. Now let's look at our Km, and in this case we would expect our Km to increase, right? We have a lower affinity now. Well, if our Km increases, let's kind of draw it out. Let's see what's going on. So we have -1 over Km. Let's say our initial -1 over Km was 1. Well, we end up with -1. If our Km increased, -1 over, let's say 2 now, we would end up with -0.5. Suddenly our value got lower, right? If we're looking at the overall like absolute value of that number, right? Our value got lower, we approached 0. So what that means is wherever our new point is on this line, it should be closer to 0. Our inhibited line might look something like that. Sorry about the bad drawing for the line. And this is the way that we can kind of remember what competitive inhibition looks like. Now, mind you, don't get tricked by the way that these graphs look. You might be shown Lineweaver Burke plots that look interesting, and you might see something that looks something along the lines of this. That does not mean off the bat that it is non or uncompetitive inhibition. You need to make sure you follow the intercepts. Always follow the intercepts, and that will guide you along the right direction because it will give you information on not only the Km but also the Vmax, okay? Well, if you have any further questions, don't hesitate to reach out. I hope this helps.